Hello everyone, welcome to COMP125 Principles of Computing. In this video we are going to continue our discussion about the software system, and we are focusing on section 3 which is about the assembly language and the assembler. So in chapter 5 we have talked about the machine language, the language that can be understood by the hardware. It is a binary language. Everything that you write needs to be written in binary, and it's going to, even when you are actually working with a part of the memory, all the addresses should be some, absolute addresses in the memory. So let me actually just, show you an example from last week. You remember we have solved this example that this piece of, for example, this pseudocode, this simple pseudocode that we have here, if we convert it to, machine language, although we actually write it in this way, but in fact, if you write it in machine language, everything needs to be written in binary. So although we actually simplify it and write, for example, move or compare, load, these kind of actually names that we gave. But in fact, these are just to simplify it for us when we are writing our example. But in the machine language, everything needs to be written in binary. So for example, for move, you would have an just assume that there is a code like, for example, 9. So this part of the code is talking about the move. These binary actual examples that I wrote here, these are just I have written just some dummy numbers here. Just wanted to show you that these are going to be a binary, binary representation. The machine language is binary representation. So you can see that it's going to be very complicated if you're supposed to write your program. Just think about it in this way, that you are a programmer, you are supposed to write a program, and you wanted to execute it on the machine, right? So that program, if you wanted to be able to execute it on the machine, needs to be written in machine language. So this is going to be very complicated because you are going to deal with all these binary representations, and it is very error prone. You can easily go wrong, and not only that, it's very hard to maintain. So just think about it in this way, that if I added something in, so for example, I wanted to add a line of code, just one line of code in between, all of these addresses are going to change. So for example, if you're going to call jump 57, after adding one line of code, all of these addresses are going to change, so it needs to be updated to jump to line 58. So maintenance is going to be difficult. Just writing at the first step is going to be very difficult. So that's why the programmer at the early stages of developing the computer, they quickly noticed that this is going to be very difficult to deal with machine language. That's why they develop another language which is called assembly language. This language, although we will see that it's kind of not very user friendly, but it's much more user oriented than the machine language. It allows you to give some names for all of the instructions. So for example, instead of the code 9, we will use that, for example, for move. We are going to actually use the code move instead of writing it in a binary representation, for example, the code 9 for that. And not only that, it's going to allow you to define some labels for the addresses, so you don't need to deal with the absolute addresses in the memory. So it's going to be much easier to work with the assembly language, although it's still not very user friendly. And at the next step in 1970s, when the very first high-level programming languages developed, in fact, the programmers noticed that even the assembly language is not really easy enough for the regular users to write programs. So they developed high-level programming languages like C, C++, and Java. So the very first high-level programming languages, I believe, have been developed in 1970s, which was C, and then after that, many other high-level programming languages have been developed. That nowadays we have many programming languages like Python, Ruby, R, Perl, Java, C++, all of these are very famous. So in this chapter, we are not going to talk about high-level programming languages. Um, in fact, in your curriculum, you will learn about high-level programming languages in courses like COMP150, 152, COMP155. All those courses are, you will learn about the high-level programming languages. So that is beyond the scope of this course. I'm not going to talk about the high-level programming languages. In this section, we are going to just talk about the assembly language, although this assembly language that we will explain is not, in fact, something that is used in actual computers, but this is something that you can get the idea that how the assembly languages can be actually developed for different, hardwares. Okay, so this figure also shows the continuum of programming languages. It is showing that, okay, if something will be executed on the machine, it needs to be written in machine language. So programmers noticed that it's very difficult to write in machine language, so they developed the assembly language. But yet, assembly language is still, we will see, I'm going to show you a couple of examples, and you will notice that, in a regular basis, it's going to be difficult even to write programs in assembly language. That's why in the next step, high-level programming languages like C++ and Java have been developed. But yet this part, which actually are going to be more difficult, and they are more close to what the hardware is going to understand, is called low-level languages. This part is going to be called high-level languages. You can see that I put even the pseudocode as a language here, although the pseudocode is not, a programming language, but this is a language that is understandable by any programmer. When you write a pseudocode, your algorithm in terms of a pseudocode, it's just like a universal language. Every programmer on the world will understand that. And of course, on the very high level, we have the natural languages like English, Spanish, Arabic, any natural languages that we speak on that. So I can actually explain an algorithm to you in in English. You can understand it, although this is very high level and it cannot be really directly be executed on the machine. So it's just like I will give you the algorithm, I explain it to you, you write a pseudocode, then it's just like a step by step. You write a pseudocode, so a human will convert an explanation of an algorithm in terms of pseudocode, and then pseudocode can be actually translated to high-level programming languages. Then from high-level programming languages, this is the task of compiler or interpreters, which all of them are going to be a kind of software system, that some applications that you install on the computer, and they will take a program that has been written in Python, in Java, in C++, and convert it to assembly. Then the program that has been written in terms of assembly language will be converted to the machine language. So this is the job that will be done by the assembler. So the assembler is going to be a piece of software system that will take a program that has been written in assembly language and will translate it to machine language. So this process has been explained here. For now, we will assume that the user will write the program in terms of assembly language. Okay, so the user will write a program in assembly language. This program can be stored in any file, like we can actually store it in using any text editor. store it on the computer, then call the assembler. So assembler will take the source program. So be careful, we call this part a source program. So that program that you write it in assembly language is going to be called source program. Source program will be passed to the assembler. Assembler will translate the source program into machine language, and that is going to be called object program, or sometimes object file. We'll call it object file. The object file again is a file will be stored on the computer. Then the loader will be called. Loader again is another piece of system software that the task of loader is to take a program that has been written in machine language. It will load it on the memory. Okay, it will load it on the memory and set the base, the main memory. For example, it will load it on memory at address 0. Then it will actually trigger the hardware. Okay, so the program will be loaded on the memory, and then the hardware will be triggered. This is also the task of the loader. So the hardware will be triggered and it will actually execute the program. So from this point, you know that how the hardware will actually just execute the program. All of that, 3 steps of fetch, decode, and execute. Remember, we have explained it in chapter 5. So those 3 actually steps will be executed in this part by the hardware, and the program will be executed. The result will be actually available on the memory. Then at the end, it is going to be the task of the GUI, for example, to go and take the result from the memory and show it to the user. For example, if the result is supposed to be shown on the printer, it will be printed on the on some paper, or if it is going to be represented on the monitor, it will be actually displayed for the user. So this is the general overview. That's what's going to happen. But what we are going to focus first is how we can actually write an assembly, a program in terms of assembly language. So I'm going to talk about assembly language first. Then in the second part, we are going to talk about the assembler, that how the assembler will, translate a program, a source program, to object file. Okay, so in all of the examples in this chapter, we are going to use a set of instructions that these instructions can be executed on the hardware. So this is a limited set of instruction, exactly like that set of instruction that we have talked about in chapter 5. In fact, this this figure, which I believe this is going to be the figure 6.5 or 15, I don't exactly remember, but anyway, this is in section 3 of chapter 6. It is coming from chapter 5. This is exactly like the table that we have discussed it and write our example using this set of instruction in chapter 5. So you can see that I have 16 different operations: load, store, increment, add, subtract, decrement, compare, different actually type of jump, a regular jump greater, jump equal. So you remember these are going to actually be able to work. You can actually work with them with compare to be able to write down the different condition, or for example when we are writing a while loop. And we also have 2 instructions for input output, if you are going to actually get the input from the user or print the output in the for the user. This we have 2 instructions for them, and at the end we have the one instruction halt that actually say that this is going to be the end of the program. So we put halt to show that this is the end of the program and there is no more instruction to be executed. So in total we are going to have 16 instructions. The name of the instruction, you can actually see that the name of the instructions that we are working on are going to be these names. Again, I'm repeating, although in chapter 5 we wrote the examples remember we wrote the examples in this way, like the load, add, store. But in fact, we just wrote it because it's more readable for us. But what we wrote there was machine language. You remember we have actually been working on absolute addresses. But now I'm going to actually show you that in assembly language, we don't need to work with absolute address, memory addresses. We will define some labels. So let me actually show you one thing. Before I actually go to the, to jump into the examples, I wanted to again emphasize on the advantages of the assembly language. So in the assembly language, what we are going to do, let me actually show you this example. In the assembly language, the form of the instructions are something like this. So there is going to be the main operation that we work on, for example, load X, and there is going to be some label for this instruction. So every step, every instruction in assembly language is going to have three parts. The first part is the label. This is a label that this is optional. For you don't actually put the label for all the instructions, but whenever you, for example, wanted to jump to some instruction, you for example, you wanted to jump to I don't know, some specific instruction in your program, you can define a label for that instruction. And then when you are going to actually write jump to, instead of writing the absolute address, you can actually write down the label. I will actually show you some examples. So the label is optional. You don't need to write it for all the instructions, just whenever you need it. And then there is going to be the operation code. This operation code is going to be just, a mnemonic name. And you don't need to write down, for example, if the value, if the binary code for load is, for example, 11, you don't need to write 11. You can just use this name load, and all of these names have been written in this table. That, for example, sorry, I forgot that the code for load is 0 in this table. So instead of writing 0, you can just write down the operation code load. And the last part of the instruction is going to be, so for example, load X. It's going to be very similar when we are writing a pseudocode that X is going to be a variable, okay? So, but when you're writing in terms of assembly, we don't really have a variable, but we can define it in this way that X is going to be some address in the memory, right? But at the end, I'm going to show you that the assembly language will allow you to, instead of writing the absolute addresses in the memory, you can define again some label, and X is going to be, for example, some label for some addresses in the memory, that where in that address you have stored the data, the value for the variable X that you are going to work on. So again, the value of X is going to be some addresses in the memory, but in fact it's going to be converted to some label in the assembly language for us. And you are going to have some, you can actually write down the comment in your language, in your assembly language as well, which the format of the comment is just you put this to, subtract, and the rest of it is going to be comment. Just like any programming languages, when you are writing a comment, the comment will be actually ignored by the assemblers. So it's just, some description that you write it, that what does this mean if whenever you actually need to write a comment in your program. Okay, so, let me actually just, okay, the advantages of using an assembly language is that instead of actually writing in binary and using all of these binary codes, we will use these operation codes. And instead of writing, the absolute addresses, we are going to use labels in the assembly language. And the last part is that there is going to be some pseudo operations that the good thing about these are that they allow us to kind of, implement some way to have variables. So for example, when I'm going to load x, which x is a variable, there are going to be some pseudo operations that allows us to write down, for example, some value for all those variables, or the constant values that we need when we are writing our program. So let me actually just show you an example. Assume that in the program that you are writing, you are going to use the constant value 5. Okay, so this constant value 5 needs to be written somewhere in the memory, so that then later on you can actually load that value 5 into the memory and work with that. So how can we do that in assembly language? There is going to be some the pseudo operations that allows you to generate the value of 5 and write it down in the memory. So when you are writing something like, for example, the format is this, that you write it as dot data. So this is something that the assembler will understand it. So when you are writing dot data and the value 5, when the assembler reads this, it will in fact take a piece of the memory and some address in the memory and store it. Generates the value of 5, which is going to be, for example, this value, and this value will be stored in somewhere in the memory. So for example, it will actually store it in address 53, and then not only it actually just generates the value of 5 and store it in the memory, but also it actually assign this label 5. You can see that this is in fact a label. Remember this format here, that we put a label and then colon. This is going to be the syntax for that. So a label 5 will be corresponding to that memory address that the value of 5 has been generated and stored. So now the label 5 will be corresponding to the actual address 53. Later on in your program, whenever you wanted to actually use this constant value 5, you can actually refer it as the label 5. So you can see that it's going to be, making it much easier and more user-friendly than just working with some binary representation, right? So, in section actually 6.3.2, it shows you a couple of examples of how we can write an assembly language, how we can convert a pseudocode to assembly language. But before jumping into those examples, let me solve a couple of practice questions at the end of section 6.3.1 to just we need to get used to this fact that the difference between memory addresses and the value that has been stored in those memory addresses. So that's good to actually just spend some time and do these practice questions. I'm going to solve a couple of them here, and I will leave the rest of them for you as a practice. So the first question in this the set of practice questions is saying that assume we are going to have a register R and some memory cell 80 and memory cell 81. And the content of these are going to be as following, that we have just assumed that we have stored the value of 20 in the register, so that the register is available in CPU not in the CPU, I mean in the on the hardware which is connected to ALU. And in the memory cell 80, so this is going to be the address. In address 80, we have stored the value of 43, and in the memory cell 81, we have stored the value 97. Okay, so now just assume that we do this, a couple of instructions. We wanted to see that if we execute each one, what would happen? So what will be the value of all of these register and these two memory cells at the end? So if I execute an instruction like load 80, What does load 80 mean? If I actually go back to the definition in the table, it tells me that whatever is the content of address X will be loaded in the register. Okay, so it is asking me to load 80. So whatever is the content of the memory cell 80 will be loaded in the register. So after executing this line, the content of the memory cell 80, which is 43, will be loaded in the register. Okay, that will be loaded in the register. So the content of R, if I execute this line, will be 43. The content of cell 80 will not be changed. It's going to be 43 just as before. It's just loading that value. It's not changing the value of this cell. And we haven't changed the value of the memory cell 81 as well. Okay, the first instruction. The second one, again, remember, it's actually just saying that for each question, we will assume that the value of the register and the memory cell is just as written here. So the value of the register is 20, the value of memory cell is 80 is going to be 48, and the value of memory cell 81 is 97. So if I execute the store 81, again, if you refer to the table, store X means that whatever is the content of the register R, it will be stored in the memory address X. So if I go back to this line, whatever is the value of the register R, which is 20, will be stored in the memory address 81. So after executing this line, the value of register R hasn't been changed, memory cell 80 hasn't been changed, but the value of the cell 81 will be changed to 20. So when I'm writing store 81, I don't mean the value of 81. I mean, I'm actually working with the memory cell 81. Okay, be careful about it. And okay, another instruction, compare 80. If you go back to the definition, compare, the instruction compare is saying that it will, after you are applying the compare X, the content of the memory address X will be compared with the content of the register R. But it's not going to change the value at the register R or the value at the memory address X. It's going to change to actually set a couple of registers, GT, EQ, and LT. Remember, we will actually use compare in combination with these jump instructions, to be able to execute some conditional, checking a condition, like if you're writing an if statement, if you're writing a loop, you will actually use compare in combination with jump greater, jump less than, not equal, and so on. So if I execute this line, it's not going to change the content of the register or the content of the memory cell 81. So you can see that everything has been actually written as it was before executing this line. And the last line, add 81, again, if you refer to the table, it's telling you that, okay, whatever is the content of X, it will be added to the content of the register R, and it will be stored in the register R. So if I execute this line, the content of 81 is going to be 43, right? This value will be added to 20, and the result will be stored 81, so it's going to be 97. It will be added to 97. I just noticed that I have made a mistake here. So whatever is the content of the memory address 81, which is 97, will be added to 20, and the result will be stored in the register R. So the result is going to be 20 plus 97. It is going to be 117. Okay, you just noticed that even I made a mistake here when we wrote the solution, but anyway, this is going to be the result. So let me actually use solve this question as well. This is also interesting. In this question, it's saying that assume the memory cell 50 contains the value 4. So just think about it in this way. There is going to be the value 4 has been stored in the address 50. So address, content. Okay. And there is going to be a label that is assigned to the location 50. So there is going to be this label L has been assigned to the address 50. Okay, so the assembler will understand, will know that if whenever it actually see the label L, it knows that it's referring to the address 50. Okay, the question is asking that what value does each of the following load instruction load into the register R? Okay, when I'm actually executing load 50, the definition is that whatever is inside address 50 needs to be loaded in the memory. So in the address 50, we have the value 4, so the value 4 will be loaded in the register R. If I write load 4, this is just, show you that one of the mistakes, the possible mistakes that you can make. So if you mean to load the value 4, you cannot write it as load 4. This means that whatever is the content of the memory cell 4, that value will be actually loaded in the register. Okay, so 4 here is going to be an address in the memory. Okay, so not the content, not the value 4. So we don't know this question. Has it been explaining what is in the address 4? So we don't know what will be actually loaded. You can just write the answer for this type of question in this way, that the content of the memory address 4 will be loaded in the register. So if we write load L, you can see that L is going to be a label, right? And so far we know that L, the label L has been assigned to the memory address 50. So whenever the assembler sees an instruction like this, it converts L to the memory address 50. So it will load whatever is the content of the memory address 50 to the register, which is going to be value 4 here. We know that. And the last one, load L plus 1. Okay, so this is something that it might actually look confusing, but just think about it in this way, that this instruction is legal, so we can write L plus 1. And what does this mean? You can think about it in this way. For the assembler, L is going to be corresponding to the value 50, right? So 50 plus 1 is going to be the address that you are going to load the value from that address. So whatever is the content of the memory address 51, whatever is that content, which we don't know it, that value will be loaded into the memory. Okay, so I believe you actually just remember and working with this type of actually instructions. Now we can actually talk about different examples of writing a program in terms of assembly code. I'm going to start with simple examples, like for example, writing converting a simple line of pseudocode, like set the value of I to 1. Okay, I wanted to see that how we can write a assembly code for this. Or for example, add 1 to the value of I. It's just like incrementing the value of I, right? We wanted to see that how we can write them in assembly language. So if you want to set the value of I to 1, you need to actually do a couple of things. If you look at the table of instructions that I have, you can see that I have I have a limited number of instructions here. I have load, store, clear. I actually just only be able to actually use this set of instructions here. So if I wanted to load 1 to the a variable I, first of all, I need the value of I to be stored somewhere in the memory. Okay, so I need to have some memory cell in the memory that that is corresponding to the value of I. Then I need to actually have the value of 1 to be stored somewhere in the memory as well. Okay, so for I need this value to be stored in the memory. The value of 1 needs to be stored in the memory so that I can actually load 1 into the register and then store that value into the memory corresponding to the value of I. Okay, so these are all the steps that I need to do. So a couple of things that I need to have is that, first of all, I need to use this, remember this pseudo operation instructions that using this instruction data, I will actually define some label that I'm going to actually just give it a name I, and you can store any value as the initial value for I. It doesn't really matter because you are going to actually just set it to 1 later. We usually actually just set all the values if it is by default. So you just created a variable, we just give it the value of 0. So I need to write down an instruction like this at the end of my my code. So this is something that I need. Not only that, I need to have something like another instruction to store the value of 1 somewhere in the memory, right? Again, I'm going to give it a name. You see that for the name of these actually for the labels, I'm using some meaningful name, just like when we are writing the pseudocode. Again, using the .data and giving the value of 1. Okay, so these 2 lines are required to make sure that you have these values stored in the memory. So some spaces in the memory have been preserved for the variable I and for the constant value 1, which I'm going to actually work with that. After that, I can actually now write the 2 instructions to set the value of I to 1. So it will be load 1. So what would happen here is that 1 is going to be the memory address corresponding to, we don't really work with the absolute addresses. I don't know where it's going to be stored in the memory, but I know that it will be stored in the memory, and the value that will be stored in that is going to be 1. Okay, so it's just like the value 1 will be loaded in the register R. Then from the register R, I can store it in the variable I. Where is the variable I? Again, but that variable I needs to be stored in the memory. So I can write it as store I. Okay, so again, this I is going to be a label, which is going to be some addresses in the memory. And this line will actually make sure that the assembler will take some space and will assign actually the label I to that space, and that space will be preserved for this variable I for me. Okay, so this is going to be, if I'm going to translate this line into assembly, I need all of these 4 lines. Okay, so let me actually just write down another translate the next instruction. The next instruction is saying add 1 to the value of I. If you look at the table, you can see that I have some instruction here that is increment the x. Okay, so whatever is x. So if you are adding just 1 to an integer variable, you can use this instruction instead of using the add. So for that one, now I know where is the value of I, right? I have already actually take some space for that. So for that one, what I can do is just, I can write it in this way. Increment, oh, I forgot, increment, let's just writing it in. Increment I. Okay, and that's it. It's going to be all of these two instructions will be actually written in this way. Okay, so load one, store one, and this one will be actually just translated as increment I. And don't forget that we need these two lines as well. When we are writing in assembly, we have to, if you are working on some constants, if you are working on some variables, everything needs to be stored in the memory. So I need one line of the instruction dot data for each one, and don't forget about the labels as well, defining the labels. Okay, let me actually show you one more example. So another simple instruction, like a equal to b plus c minus 7. It just actually written in usual high-level programming languages, which means that the value of b plus c minus 7 will be executed, will be evaluated, and then the result will be stored. The result of this will be stored in the variable a. Okay, so how can I write it in terms of assembly? I need to, first of all, just take care of all the variables and constant. How many variables and constant I have? I have a, b, c, and 7. So what I'm going to actually do here is that I'm going to define 4 lines of dot data instruction and giving all these labels. So one label for a, one label for b, c, and a label that's called 7. The initial value for a, b, and c, I will actually just write down 0. Later on, anything can be actually just loaded on that. I don't care about it here. It's just like by default, I will give them the initial value 0, because here the question hasn't been asked me anything. And the value 7 that has been actually stored. Okay, now I'm going to execute this line. I need to first evaluate b plus c minus 7. Okay, how can I convert it to the assembly language? I need to do each of these operations one by one. So what I'm going to do is I'm loading the value of b. The value of b will be loaded in the register. So it's just like the inside the register will be the value of b. Then if you add C, the content of the memory cell C will be added to the register, and it will be stored in the register. So it's going to be B plus C. The content of R will be B plus C. Then I wanted to actually just subtract the value of 7 from that. So what I'm going to write is, using the command subtract, you can see that I'm just following all the instructions that I have here. So subtract x, whatever is the content of the memory cell x will be subtracted from the content of the register R and will be stored there. So it will be actually just minus 7 at this step. Okay, now I need to actually just store the content of the register R inside the variable a, inside the memory cell corresponding to the variable a. So I'm going to write it as store a. So this is going to be the full set of instructions corresponding to this line. Now you can see that why we are saying assembly language is not going to be very user friendly. When you are writing in high-level programming language, definitely writing this line is going to be much easier than writing all of these 8 line of codes here, and it's going to be really complicated. But of course, that's still way better than writing in terms of machine language. Okay, here is another example that has a couple of actually input, output instruction, and also if condition. Okay, first of all, before actually doing anything, you should look at your pseudocode and find out all the variables, all the constants that you need to work on. If you read them, you can see that I have one variable for x and one variable for y. Again, I just noticed that I made a typo here. This is going to be actually y. So you get the input value for x. for y, and there's no more variable or constant. Okay, so I need two dot data instruction to get some space for x and y. I have defined the label for them corresponding to actually this capital X and capital Y. Okay, input the value of x. Okay, this line, there is going to be some instruction for that. You can see that there is this in x will take the value from the user, from the input, and store it at the memory address x. So there is going to be just one line of code for this one. Okay, so this one will be actually just converted to in x. This one will be converted to in y. Then I need to actually compare the value of x against y. And if the value of x is greater than or equal to y, this line should be executed. Otherwise, this line should be executed. If you look at the table of instruction, I don't have anything for, I can compare the value of x against y using this instruction. So what can I do for this one is that we will load x, okay, and then write compare y. So what would happen after this line? After this line, the value of three main registers that EQ, LT, and I believe the last one was GT will be initialized. So if the value of the register R is greater than Y, I believe GT will be 1. Let's just refer to the table. It's just telling you that, okay, if the content of X is greater than the register, GT will be 1. If the content is equal, EQ will be 1. If the content is less than the content of the register, the LT will be 1. And whenever, for example, GT is 1, the rest of them will be 0. Whenever EQ is 1, the rest will be 0. Whenever LT is 1, the rest will be 0. Okay, so let's get back to that example. We have loaded X to the memory. When I'm comparing Y, it's just like you are saying that if the value of X has been stored in the register R, so if Y is greater than X, which is inside R, after compare, GT will be equal to 1. Okay, if X is greater than, if the value of Y is greater than X. Because I don't have any instruction to jump for less than or equal or greater than or equal, what I can do here is that I can just think about this condition in a reverse way. So if X is less than Y, in fact, you wanted to execute the else part, right? So what can I do here is that I can check this one. If GT is 1, okay, if GT is 1, I wanted this line to be executed. That's why it actually written in this way, that jump GT, go to the label next. It's just like if the value of Y is greater than X, I want you to jump to the label next. Okay, label next is a label of an instruction in the memory, so which is going to be this line. So it's just telling you that instead of working with absolute memory addresses, just work with this label next. So if the value of Y is greater than X, execute this line, which is exactly telling you output the value of Y. Okay? But if it is not, if the value of Y is not greater than X, so what would happen is that after the CPU reads this line, the control unit reads this line and notice that, okay, the value of GT is not 1, the next instruction by default will be executed, right? Which is going to be out X. This is exactly what I wanted to execute if the value of X is greater than or equal to Y. Okay, so out X will be executed. After out X will be executed, I don't want to actually continue. I wanted to actually jump out of this loop, right? So that's why after this line we have this jump, which is telling you that, okay, jump to the label done. I put actually the label done exactly after this label next. So whatever is the content that we are going to write here will be translated and written here. Okay, so this is going to be the full translation of this instruction. I mean, this simple pseudocode. Okay, let me just show you another example here. We wanted to, this is one of the examples from chapter 2 that we wrote a pseudocode from there. No, I'm going to actually just show you the pseudocode for that, and then we are going to convert it to the assembly language. So what is the problem? We wanted to write a pseudocode, a program that reads a sequence of numbers, gets these numbers from the user, from the input, and all of them should be non-negative. Okay, so whenever you find a negative number, the program will stop, will terminate. We wanted to get the summation of all these non-negative numbers, and whenever we get a negative number, we will stop, just print out the result, the summation of all those non-negative numbers that we have seen, and print that all those results out and terminate. Okay, so this is showing you the pseudocode for that. Okay, I'm going to calculate a summation of a couple of numbers. Of course, I need a variable for sum. That variable will be initialized as 0. Okay, set the value of sum to 0. I need another variable to get the data from the input, right? I'm going to call it n. And I need to actually started getting the values from the user. So you get the first actually value n from the input, and then I need a loop because I don't know how many items are going to be entered by the user. I just need a loop to continue until the value that has been inserted is still positive. So we will just need to check that if the value of n is not negative, do these two steps, which is just adding the value of n to sum, okay, and also getting the next item from the user. And at the end, whenever actually you find out a negative number, you will jump out and print the value of sum, and the program will finish. Okay, so one thing before I show you the full program here is that there are two other symbols which are important for us in assembly language. If you are writing a full program, there are two labels, a kind of actually they're not labels, they are in fact some pseudo operations, which called .begin and .end. .begin and .end, these instructions in fact are telling the when the assembler translating your program, it started from .begin and ends at .end. Okay, so it's just like the .begin and .end tells the assembler that where the program starts and where it is going to be end. Okay, so the full set of instructions that you are going to write needs to start with .begin and needs to finish with .end. Be careful, this is different than halt. Remember, we had an instruction halt from this set of instruction, this table here, that is telling that the execution of the program will be ended. Okay, that is different than the .end. .end tells the assembler that this is the end of their program that has been written in assembly. So you will start with .begin, write down all of your instruction that at the end you need to put halt at the end of all of the instructions that you write. And after the halt, we usually just write down all of those .data instructions that you are taking the space, some memory at the end. And at the end of all of that, you are writing the dot end instruction. So let me actually show you the, okay, this is our pseudocode, right? And this is going to be the full, the complete assembly language program, which is the translation of this pseudocode. Um, Before actually I go to the details of the translation, that each line can be how we translated each line, I'm going to actually focus on these parts, that the program has been started with dot begin and it has been ended with dot end. Okay, the full piece that is the translation of the instructions, for example, from line 1 to line 8, the full instruction is here. You can see that I wrote the halt as the end of it. It's just telling that this is the last instruction that needs to be executed by the CPU, by the computer, by the hardware. Okay, and then after the halt, all of those instructions, that is those pseudo operations that's taking the space, like the dot data instructions, needs to be written here. But be careful, all of them needs to be inserted before the dot end. So dot begin and dot end is just telling the assembler that this is going to be the beginning of the full source program, and this is the end of this full source program. Okay, so know that you know the full structure. Let me actually just go to the details of the translation. Let me just do a little bit of cleanup here. But I believe it's good to actually just put some structure to show the distance between, these are the set of the dot data instructions. Look at the pseudocode. In the pseudocode, how many variables and constant values we need? I need one variable, variable sum. I need a variable for n, which is taken from the input, and you can see that I'm checking that the value of n is negative or positive. So for checking that if n is negative or positive, you need to compare it with 0. If it is less than 0, it's going to be negative. So that's why I need a variable for some memory address, memory cell for constant 0 as well. So in total, I need to store 3 different constants. I need to store two different variables and one constant, sum, n, and 0. I'm giving these labels sum, n, and 0. I'm initializing the sum and n with 0, and of course the constant 0, I want it to be 0. Okay, so I'm done with the data instructions. Whenever you are doing all of these examples, first write down your dot data instructions, and then started translating the full pseudocode. Okay, the first line is we wanted to set the value of sum to 0. Okay, to set the value of sum to 0, if you look at the instruction, the set of instructions that we have here, in fact, there is a very useful instruction here, clear x. What does this clear x do? It will actually just make sure that the content of memory cell x will be set to 0. Okay, so whenever you are going to, for example, put 0 in some variable, you can actually use this instruction. It actually makes it much easier than loading 0 to the register and then storing that. Okay, that's going to need 2 lines of code, 2 instructions, but this one will be done in just 1 instruction. So that's definitely going to be faster, right? So we translate the first line, set the value of sum to 0. We translate it as clear sum. Okay, the next line is just saying that, okay, take get the first value of n from the input. So I have an instruction in n, so you get some value and store it in the memory address n, that label n that we have actually just reserved for this variable n. And then I need to compare the value of n with 0, and if it is not negative, in fact it's going to be if n is greater than or equal to 0, I would execute this part, the body of the loop. But if n is negative, I wanted to actually jump to this part. Okay, so now it's clear that working with this one is going to be much easier. What I need to do is I need to compare n with 0. How I'm going to write it? I will load the value of 0 into the register, then write compare n. So if the value, the content of n is less than the content of r, which is going to be 0, then the register LT will be 1. Okay, so I will write it in this way, that if it is negative, I wanted to jump out of the loop, right? Okay, so in that case, we can actually write it as jump LT to the label neg. What is this label neg? Later on, I can actually just, because this is assembly language, I can write it on paper, right? So just write down some label and write down whatever you wanted to actually execute at the end. And you don't need to be worried about the address. Later on, you just write it down here, right? Okay, so the label neg, and you can give it any name. It doesn't really matter. But if the value of n is greater than or equal to 0, the next instruction will be executed. What you wanted to do, you wanted to add the value of n to sum and also get the next value for n. To add the value of n to sum, again, I have to load the value of sum to the register, then add the value of n, and then store inside sum. So these 3 lines are going to execute this line, that set the value of sum, set sum to sum plus n. And then you wanted to take the next value of n, okay? And this is going to be the end of the body, right? You wanted to actually just go back to the beginning of the loop, again, compare the value of n to 0. If it is not negative, continue. If it is negative, jump out and come to here. So what I can do here is to just jump back to the beginning of comparison and jumping, which is going to be this line. You can see that I have defined another label here for again. It's just actually just write it as again, so that it's going to directly jump back to this line. Again, the value of 0 will be loaded into the register, and then it will be compared to the value of n. If the value of n is less than that, it will jump to where? So now you can actually put your label neg, which is going to be the translation of the last line, which is going to be just printing the value of sum in the output. Okay, and at the end, I will put the halt. So this is the full instruction. Just don't forget to put the dot begin and dot end as well. So I have this piece for all the variables and constants. I have this piece which is the translation, the full translation of the instructions, the dot begin, dot end, and this is going to be the complete assembly program. This is a assembly program that we can write and pass it to the assembler. Okay, again, at the end of this section, there are a couple of practice questions. I have write down the solution for a couple of them, which I found them more important. Okay, you can actually read them later.
try them as a practice and then refer to the solutions that I wrote here. Okay, I'm going to finish this section by just talking about the translation and the loader. So whenever we actually write down our source code, the source code will be passed to the assembler. Remember this figure. Whenever you write down your program in assembly language, this is going to be called a source program, right? So for example, you write down something like exactly this one. This is going to be the full program, will be written in an editor, in a text editor, will be stored as a file, and it will be set, it will be actually sent to the assembler. Assembler will be invoked, okay, then it will translate this program into the machine language, okay. After we are done with the translation to the machine language, then the loader will be called. The loader will load it into the memory, will trigger the hardware to actually execute the full program. Okay, so this last part of this section is actually talking about the assembler, the tasks of the assembler, how the assembler can actually translate some program that has been written in assembly language, converted to the machine language. So the assembler needs to do a couple of things. It needs to actually convert all those labels into some memory addresses, and it also needs to convert all those operation codes into their binary representation. These are the two main actually tasks of the assembler that are complicated. It also actually needs to, for example, this part, it needs to also generate these values and give them some address in the memory. So this part also needs to be done by the assembler, and it actually needs to take care of these labels. So whenever it sees some, it will be referred to the corresponding memory address for some that it actually just generated. So all of this needs to be done by the assembler. So how the assembler can actually do this? So the main two tasks that we have is first converting the symbolic operation code. So for example, if I'm writing something like, look at this example. If I'm writing something like clear, it's corresponding to some code, right? It needs to be converted to some binary representation. How the compiler can do it, it can actually just do it using a table. Remember, we have a table that of all of these instructions will be written in terms of those mnemonic names and also the binary values. So for example, add, clear, compare, and so on. So this part is kind of easy. The compiler, the assembler just needs to read each line and say that, okay, the first line is clear sum. So clear needs to be converted to its binary code. It just needs to look at the table, find the value clear, and find its corresponding binary value, and just in this way it can actually simply translate each instruction, each operation code of instruction that we have. But the only actually important, complicated thing about this search is that, think about it in this way. You write a program, that program probably is going to have I don't know, maybe a couple of thousands of lines. For each line, for each instruction, you need to refer to a table. You need to search in your table. If you are doing a sequential search, look at all of the instructions, it's going to take quite sometimes, because the number of instructions that you need to translate at the end is going to be a couple of thousands of instructions, and the number of instructions, the table of instructions, is not as short as just 16. Usually in the actual hardwares, the set of instructions that you have are going to be 500, maybe 300s to 500s, right? So it's going to take a long time. What we can do is we can store the instructions in a alphabetic order and use binary search. Remember, we have talked about the sequential search, which the time complexity for the sequential search was order of magnitude, it was linear, but for the binary search it was log of n. Remember, and log of n was much faster. So you can actually refer to your textbook. It's actually explain it in terms of some number to gives you some sense that how much faster it will be if you use the binary search. And again, it's just emphasizing on this fact, you need to design efficient algorithms, because in practice they are going to make a big difference, when we are using them in daily basis. Okay, so the first step, the first task that the assembler needs to be done is just translating the operation code. The second actually task that the assembler needs to do is translating those symbolic addresses, those labels, into actual binary addresses, those absolute memory addresses. Okay, this one is not as simple as using a table for translating the operation code. The fact is, when we are writing or assembly code, there is no table for saying that which of these labels are referring to. So for example, the label again, what is the value for this label again, where this line has been stored in the memory. We don't know. This is something that the assembler needs to do it. So assembler needs to basically to do this task in 2 steps, in 2 rounds. The what actually assembler do in the first round is that, just think about this simple example. Just assume that I have this piece of code, assembly written in assembly language. Okay, these are the instructions. Okay, and these are the labels for them. The assembler will read the full instruction, and whenever it finds a label, it actually stores it in a table that we call it a symbol table. So at the end, all of these instructions are supposed to be converted into binary representation in machine language, right? So all of these instructions needs to be stored in the memory. Okay, so for each of these instructions, there is going to be some address. So we are going to define some location counter and say that, okay, the very first instructions will be stored at memory address 0. The second instruction will be stored at the memory address 1. The third instructions will be stored at the memory address 2. So it just reads each line in the assembly code, in the source code, read each line and just increment this location counter as well. Whenever it finds a label, so for example loop will be corresponding to the value of the location counter 0. So this pair, loop and 0, will be stored in a symbol table. Okay, so it actually just goes down until this line. It actually finds done, so which is corresponding to the line 7. It's just like it's corresponding to the address memory 7. So it stores done and 7 into the symbol table. Also, after it actually is done with the full set of instructions here, it will also read all of those dot data instructions as well. So it will read the dot data instructions. It will store those values zeros as well. Okay, and for each of them there is going to be a label, right? So the label x will be corresponding to the memory address 9. Okay, the label y will be corresponding to the memory address 10. All of these labels with their address values will be stored in the symbol table. Okay, so now after the end of the first round, we are going to have the symbol table, and everything is going to be much easier for the second round. Okay, in the second round or in the second pass, the assembler will just read each instruction and convert the operation code to the binary using that the table of instructions. And if there is a label in front of your instructions, that label will be written from the symbol table. So the translation is going to be quite easy. It also actually just will do the dot data pseudo operations as well. So this table, this figure is just summarizing all of these steps. So it's just like assume that you have a piece of code written here. What the the assembler do is just it will read each line, and corresponding to this line it will write down an instruction which is written in machine language. What is the format of the machine language? The machine language is going to have 16 bits, that the 4 bits is going to be the operation code. This 4 bits here, it's going to be operation code, and the rest is going to be the memory address. So an instruction like in X just means that find the corresponding code for in, which is, for example, going to be 8 plus 4 plus 1. This is going to be 13. Okay, 13, this is the binary code for that. And then X is going to be some address in the memory, right? Where is that address? That address is actually going to be stored in address 9. Okay, address 9, and you need to actually put 0 because you need to make sure that this is full 12 bits. Okay, so this is going to be that address part, this is going to be the operation part. So this line is going to be converted to this machine language, and it will actually just go through all of the instructions one by one and translate it to some binary representation. So this is the full program that will be passed, will be stored as the object file or the object code, and then it will be actually passed to the loader. The loader will be called. It will load this piece of code into the memory from the address 0, and then it will actually just invoke the hardware. The hardware will execute the program. So this is the actually finishing the section 6.3, which is going to be the end of this the content for this week.